Okay, 9F, conditional probability. So what's conditional probability? Like for a random experiment, for example, I toss a coin, throw the dice, or predict weather tomorrow, I don't know any information. So it can be a random experiment or random check, random guess, like it's very random. But now is conditional probability is I know some information in advance. For example, I saw a question really good is I have 3 cards. Well, you can think about this question by yourself after I finish this. Okay, I have 3 cards, well, same size. Well, I draw not to the same size, but like it's same size. Okay, identical cards. Put in a box. I have 2 sides blue for the first card. I have 2 sides green for this card, and I have 1 side blue and 1 side green for the other card. Okay, 3 cards like this. And now I randomly pick, what I'll do is I'll randomly pick a card and put the card on the table. Okay, I'll randomly pick a card and on the table. So it can be this side or can be this side. I just randomly put on the table. But now what information I have is the card. Oh, I'll ask you first. What's the probability I will get the card with 2 sides blue? What's the probability I'll get the card with 2 sides blue? 1/3, right? It's 3 cards identical and one of the cards satisfy what I want. So it's 1/3. But now the information I have is I pick a card. I put the card on the table. It shows me blue. Okay? It shows me blue. That's some information I already know before I will talk about the which card I get. Okay? So show blue on the table. This is some information I know before we talk about the probability of the card I get. And I'm asking, what's the probability that I get card 1? Let's say there's card 1, card 2, and card 3. Okay. It shows me blue and then asks me what's the probability to get the card, like what's the probability that this card will be card 1. Okay, so this is the question. But like we don't need to do it now. Like after I finish this exercise, we think about it. But do you think this probability will be larger than before or smaller than before? Or same as before? Like we said 1/3 to get the first card. Why larger? Only left with 2 options, right? What do you think the probability will be? Half? Half? Okay, I'll tell you it's not half. 2/3 is correct. Okay? But like, you need to think about how we get it. Like I'll give you a hint, tree diagram will be better to do that. But like, I haven't talked about the formulas to you yet. We'll talk about the formula first and then come back to this question. But what you know is, for some extra information given to you, that will increase or decrease the probability. It will change the probability compared to a random guess or random pick. Okay, so that's the point I want to make here. So conditional probability is you know information in advance. So normally when you know there's a conditional probability, the word given or knowing that will be the key words you have when it is a conditional probability. So giving you the card on the table is blue. And then, comma, what's the probability you get the card with 2 sides blue? So that's obviously show you that's a conditional probability. You need to think about the conditional probability formula. Or it can say, knowing that, say we have a group of students and some aged 12 above and some age 14 above. Let's say we have a group of kids like that. And then I'll say, knowing that the kids you pick is the age 14 above. So you know some extra information. It only restricted like the group into the group of 14, not including those with 12 to 14, those group. Okay. So that's conditional probability, and those two words are the key words to showing you that's conditional probability. So what is conditional probability and what formula? Well, what is conditional probability I've given to you, but now I'm talking about the formulas for conditional probability. So I want to talk about some events A. For example, I also talk about, like the example I give you, I also talk about event is get card 1. Okay. So the probability for the example I have is get card 1. And the actual information I know is show blue on the table. Okay, show blue, like one side shows blue on the table. So this is another information I have. So this is, put is what you want in the front given what information you have at the back. So it's A given B. Okay, so it's A given B. What is the formula we have is, when we write probability A given B is probability A intersects B divided by the probability of B. So the probability I will have for this one is, well, showing blue is one side with blue, and I want get card 1, which means both sides blue. What's the intersection between them? What do you think the intersection between them will be? Well, I show one side blue, and then get card A got two sides blue. What's the intersection between them? Okay, I have one side blue. I have one side blue. Okay, one side blue. Which two cards I have talked about? 1 or 2, right? So for events B, I 1, 3. Like for events B, I can have either card 1 or card 3. Showing two side blue, which card I'm talking about? 1. Okay, so event A is 1. Okay, so event B is 1 and 3. So what's the intersection between that? 1. Okay, so events A means I want to get card 1. Events B means I can have either card 1 or card 3. So the intersection is card 1. Okay, so A intersects B can still be that A. Okay, can still be that A because A is a set included, element included in event B. So I will do the intersection. So according to this question, still the top intersection is still get 1. Okay, get card 1. And now I need to work out what's the probability. Well, remember get card 1. The probability to get card 1, just random get card 1 is a third. Right? Remember that the top is just a third. Just randomly get a card. So that's a third. Now I want to talk about show. I pick a card and this card can show blue. Okay, this is the probability I want for B. Okay, because B is showing blue on the table. What's the probability of showing blue on the table? Okay, what I pick a card, I put the card on the table. How many stages is that? 2 stages. Okay, I need to pick a card first and I randomly put one side on the table. Okay, it's a 2-stage experiment. That's the hard part for this question. I can pick card 1. So card 1 will only show blue. Okay, it's a tree diagram. I can think about that as tree diagram. I will get card 1, or I will get card 2, or I will get card 3. They are all like a third of the probability. Okay, so a third to get 1 or 2 or 3. So I can only show blue and blue. Right? Blue, because the first card is only blue. So the probability to get a blue, if I pick card 1, the probability will be 1. Okay, if I get card 2, that will only show you green, right? The probability will 1. The probability to get a blue or get a green for the third card is a half and a half. Okay, half of the chance to show blue on the table, half of the chance to show green on the table. So first of all, I pick the card 3. In my hand, I can put this way or I can put this way. So it depends on like random pick. Okay, half and half. So now the probability of show blue will equals to a third times 1 plus a third times a half. Yes, yes, like this is the probability showing blue. So this will show blue, this will show blue. I don't care which card I pick. So I will have, that's 2 on 6 plus 1 on 6, which is a half. 3 on 6, which is a half. So the probability showing blue will be a half. Randomly pick a card and I put the card on the table. So that's 1 on 2. So now this question will be, okay, as 1 on 3 over 1 on 2. That gives me 2/3. Okay, that's why I said 2/3 is the correct answer. So how I can write this? I will write this as the probability get 1 given that show blue. Okay, so that equals the probability of still get 1. Because you get 1, you definitely show blue. So probability of getting 1 over the probability show blue. Okay, by the formula A intersects B over the probability B. Get 1 is a third. Okay, with no information, just want to get B, that's a third of the probability. Over a half, which is the probability you can show blue. And now that's 2 on 3. That's 2 on 3. It's a hard example, but I think this example is interesting. Can make you think about it. Okay, so that's the conditional probability. I have restricted that, like I totally restrict the case for number 3. I won't have card number 3. So it can, number 2. I can only have number 1 and number 3 by this card showing blue here. So I have restricted, but showing blue is already an advantage for card 1 because you show blue, which means a larger chance you get 1 already, because to get 3 you have blue or green. It's not showing green, so it's showing blue. So that's why it's not a half of the chance, it's 2 on 3 of the chance to get card 1. Yes? Any questions? No? So that's the conditional probability. Okay, that's the conditional probability. This formula will be helpful for all the year 12. Well, I talk about, like I said, probability here is super easy in year 11 and year 12 will be really hard, but all the basic formula doesn't change. Okay, for example, what you learn here, that's what you have. Okay, that's just conditional probability. This formula will be true, doesn't matter how the question is changing. This formula is always correct. So probability A given B is probability A intersects B over the probability B. This formula will always true. But like this part, well, I don't really want you to think about that part, but like that's when we talk about something, when we have equal likely events and then it's countable numbers. We are talking about 1, 2, 3, 4, like those numbers. Then we can think about like that's the number of A intersects B over the number of A. So instead of the probability of A intersects B over the probability A. So but like this is not something really useful in year 12. So the correct formula will only be this half. Because everything we talk about here is discrete event. But if you have continuous event, you can't use that one. Like when you have continuous random variable, like things can take all the infinite values in year 12, that's not working. So you can only use the first half of the formula. So just remember the first half of the formula, that will be good. Now, what's the difference between probability A intersects B and probability A? So probability A will be basically, you think about area, will be this area over this area. Okay, if you think about the area wise, if the area is in proportion, that will be the red area divided by what can happen in total. Okay, but for A given B, you know B is happening and you want A happen as well. Basically, you reduce the chance can happen into this section. So it's the area of here divided by this area. Okay, it's the area of that divided by the area of B. Because you have eliminated all the possibilities outside B. B already happened. Okay, that's something you know. B already happened. So then you want to talk about A, the probability of A happened. It will be A happen will be that intersection part and then over the total area of B. So that's the probability A given B. Okay, let's have a look at example 1. I'm not going to do all of the examples. They are very easy. Well, I like my example given above. This is a better example to consider about like the given probabilities. But example 1 is kind of boring compared to that one. So in Stephen's class, 12 students study Chinese and 20 students study French and 8 study both Chinese and French. Given that a student in his class study Chinese, given a student study Chinese, what's the probability also study French? So the notation, I'll care about the notation more. This is talk about the probability. What is the probability learning French? So probability of French given learning Chinese, given probability of Chinese. And then I can say that's because it's talking about numbers, I can say that's the number of French intersects Chinese over the number of Chinese. So that will be 8 over 12. Divided by 4. Divided by 4. That's 2 on 3. Yes? Why 4? Yeah, 12 students in the class study Chinese. It can't be Chinese only because you want French happen at the same time. Say we have row 1, row 2 students study Chinese. Row 1, row 2, row 3 students study Chinese. Yeah? And row 3, row 4, row 5 study French.
Yeah, and exactly. How do you know that these 12 students study? Is it given that they only study Chinese?
No, it doesn't say only. It just says study Chinese. It means any student study Chinese. Yeah, it's the total Chinese student.
Yeah.
So B is the same thing. So I'm not going to do B. So B is the same thing. You can try B and example 2 by yourself. This example 2, you can think about tree diagram to work on, or like any other method you like. Now let's have a think about independent events. Okay, independent events is really important. Just write a question here for you. I have that equals to that. Event A equals to 1, 2, 3, 4. Event B is 3, 4, 7, 8. Okay, my question is whether event A and event B are independent events. Okay, this is a question in VC exam, and I think it's something really good to talk about in year 11. So, well, the top one is the full set. Okay, so it's the full set, like 1, 2, 3, 4, 5, 6, 7, 8. And event A is 1, 2, 3, 4. Event B is 3, 4, 7, 8. I'm asking whether they are independent or not. So let's talk about what's independent first before we do this question. Okay, I just think this question is a good one, so I'll just put it here for you first. So what's independent events? Independent events are the events are not affected by the previous events. For example, I have a bag of candies, some black chocolate, some white chocolate. Now, let's say we have 10 black chocolate and 5 white chocolate. What's the probability of picking a white chocolate? 1/3, right? 15 chocolate in total, 5 white, so 1/3. If I pick a chocolate and eat it, what's the probability of getting a white next time? Okay, so that's the thing. You ask me what? Did you eat the white chocolate or you eat the black chocolate, right? This means the first events affect the result, like the result of the first events will affect the second outcome. Like the second one, my selection will affect that. They are dependent events. Okay, the second one relies on the first one's result. That's dependent events. For example, today is raining. Do you think tomorrow will most likely rainy as well? In Melbourne, like I can't tell, like some other random place, like not like normal place. Yes, if today is raining, there's a higher chance tomorrow's raining as well. If it's sunny, tomorrow might be sunny as well. So there's a larger probability. So they are all dependent. Okay, they are all dependent. Today's weather depends on yesterday's weather a little bit in some extent, not 100%, but some extent. So they are independent. What are independent? What are independent? So same box of chocolate. I just pick one and have a look at it. I don't like it. I put it back. And then I can pick another time. So this time, the first events and second events, they are totally independent. Because the probability you get, everything doesn't change. And the result doesn't, well, the second selection doesn't rely on what the first one has select. Well, it doesn't matter select a black or blue or a red. No, black or white. It will be the same probability for the next time. Therefore, examples of independent. You toss a fire coin twice and two trials are independent of each other. Because the second trial, you get the probability of a head or tail is exactly the same. Doesn't matter what you get for the first time. Or whether Lily wear a red dress are independent of whether Jack will wear jeans tomorrow. So what you wear and what I wear is totally independent. The result of you doesn't affect what I will wear today. So they are called independent events. Now, let's come back to this question. Can you tell about anything similar to that? Can you give me any reasoning here? Yeah? Which one? With replacement is independent. Without replacement is dependent. But I have reasoned all of this. Now you understand perfectly what are independent, what are not independent. But just look at these questions. They are only numbers. There's no other explanations. You only have sample space 1, 2, 3, 4, 5, 6, 7, 8. Event A 1, 2, 3, 4. Event B 3, 4, 7, 8. Yeah, but that can't be done through my explanations before. Yeah. Like my explanation 1 minute ago doesn't explain what's going on here. Okay, so therefore we need to, yes, the intersection bit. Therefore we need to introduce two formulas. Okay, they are important for year 12 as well. Okay, so last page the conditional probability is important, and this page the dependent independent is very important as well. Normally math questions, you can't reason things all the time. You can't say that's a number, I want to reason it why this one doesn't affect the other one. So I can't really reason like what we wear, how's the weather, how's the chocolate. So we need formula to help us to decide. There must be a formula. It's a black-white thing. Whether it's independent or not, it depends on the formula. So what's the formula talk about is, okay, the first formula is not common used. Okay, the first formula is not common used, but is explained more, like explained better, because it says that given you B happened already, I want to find the probability of A, but that is still equals to probability A, which means the knowing B happened already doesn't affect the probability of A. Can you think about that? That's why A and B are independent.
So these two formulas will very well start.
Yeah.
If it works, then the events are independent.
Yeah. Well, what do you? Oh, sorry. What again?
If A happens to be nothing happens, so probability is
No, they are independent. You don't talk about like at a subset or something. Like you don't talk about that. Like you just think about the probability. This is more like a reasoning thing. So, given B happened already, I'm trying to find the probability of A. But that tells you it's exactly the same as probability A. So, which means the happens of B or not doesn't affect the probability of A. There's no influence between A and B. So which means they are independent events. Okay, they are independent events. But now let's expand the left-hand side. Okay, let's expand the left-hand side. We have probability A given B is probability A intersects B over probability B. Okay, this formula is still true. Doesn't matter they are independent or not. Okay, formula is still true. And then you make that equals to probability A. So therefore, we have created the second formula is probability A intersects B equals to A times B, because you transfer that to that side. Okay, because that's equal, then probability A intersects B equals to probability A times probability B, which is the second formula. It will happen at the same time. If the first one is true, second one must be true as well, because it's basically coming from the same formula. But the first one is through reasoning. Okay, it makes sense a lot. B happen, find A. That's still the probability of A. The whether happens B or not doesn't influence the probability of A. So they are independent. That's through reasoning. Then through formula, I just expanded. Okay, so what we have is probability A intersects B equals to prob A times prob B. That's come from this one. Okay, that's come from this one. But this is a common use one. Okay, we normally use the bottom one. Okay, we normally use the bottom one. So that's a common use one. Alright. So let's go to the top. Another thing. Okay, please listen. Another thing. What are mutually exclusive events? No intersection, right? So mutually exclusive, I'll just write here. So I will use a Venn diagram to show that. That will be event A and that will be event B. So they are mutually exclusive. Do you think they are independent events?
Yes.
Why? So if it's independent, I'll say prob A intersects B must be prob A times prob B, right? Yes? I'll say that. What's A intersects B through the graph?
0.
Do you think your right hand side will be 0? Unless A or B will be 0, right? Unless we don't have A or we don't have B, and then we don't have two events. There is no mutually exclusive. So it's not going to be true. This formula will not satisfy. Okay, so it's not equals to. It's not true. Okay, it's not true. So mutually exclusive events and independent events, they are not equivalent to each other. This is a place students always confused. Okay, so mutually exclusive events are not independent events. It's almost never independent, because mutually exclusive means intersection is 0. Then right hand side want to be 0 as well, either A is 0 or B is 0. So if A is 0 or B is 0, that means there's no events A or no events B. There's even no two events.
But then if we have mutually exclusive events like Foxy, 5, and then I being handy about the 2, they're not dependent.
They can be dependent. Like you can't predict they are not mutually exclusive. Mutually exclusive means they can't happen at the same time, right? But what you said happens at the same time already.
Oh, okay.
Mutually exclusive events means they can't happen at the same time. So something can't happen at the same time. But something can't happen at the same time means they are dependent, because this happened, this one can't happen. This already dependent already.
Okay.
Can you think about that way? They can't happen at the same time, so which means there are some relationship between them. This happened, the other one can't happen. They are dependent. Yeah? I'll think about a good daily use example for you and then explain that next lesson. I can't think about a good one. This is really mad thinking. But I'll think about, or anyone can give me a good example when something can't happen at the same time, but they also independent. They are dependent. Okay, let's finish this one first. Okay, I'll just do one more example here. I want to talk about whether it's independent or not for this question. Okay, I want to talk about whether they are independent or not. So I want to write a proper proof. Okay, I want to write a proper proof. Be careful with words, it's a proper proof. I think half of you will start with the line probability A intersects B equals to prob A times prob B. I'm not sure whether you will do that, but it's a very, very, very terrible thing to do that. It's a terrible thing. Why? You don't know. Do you know A intersects B will equals to A times B? Do you know that? No. Then why you write this line? Why is true?
What you told us?
No, I haven't told you that's true. No.
Don't do that to us.
Can you read the first line in the box?
Oh, we don't know if it's independent or not.
Yeah, we don't know. The box says two formulas that can check whether the independence or not is these two formulas. Okay, so all I should say, if they are true, then that's independent.
So write if in front of it.
If, there should be an if. If is that. No, you check using this formula doesn't mean you directly write the formula there. You check whether it's true or not, whether the formula satisfies or not. Whether it's a true formula or not. So hard to talk, everyone. Let me finish. That's something I see students get wrong every single year, and it's not one student. Every single year. I don't know how I can make you remember. You can't write the statement before you do any calculations. This is a statement line. You can't just write your conclusion at the beginning. I make the conclusion this is true. And then after all your calculations, say, oh, sorry, it's not true. And I change my conclusion in the front. Conclusion needs to be in the end. So we think about the left-hand side only. We will think about what's my left-hand side equals to. My left-hand side probability A intersects B. Intersection is that, which is 2/8. That's 1/4. And I want to think about what my right-hand side equals to. That's 4/8 times 4/8. That is 1/4 as well. Okay, even though they are equal, you can't write they are equal at the beginning because you don't know at that time. You only know after you do the calculations. So you do the calculation for left-hand side, you do the calculation for right-hand side, then you compare them, whether they are the same or they are not the same. You make the conclusion here.
You're allowed to assume that if they do equal.
You're not assuming anything yet. You're not assuming anything. You basically calculate left-hand side and right-hand side.
But then you know that if the left-hand side and right-hand side are equal, then
oh, that's a true formula because what I can write here is probability A intersects B equals to prob A times prob B. You don't need to.
You're allowed to know that.
You know that. You know that. You can't write it as a conclusion at the beginning. Yeah. You just don't write it at the beginning step. When that's true, you know that's independent. So you will say A and B are independent. And you can't see anything after that. Okay, so your conclusion is a conclusion step, is in the end. It's not at the front. Even though it's true, this is true, you still can't write it in the front. Your logic is wrong. Okay, you're not assuming it's equal or you're not assuming it's not equal. It's after, because I don't need to assume anything. I can calculate. I can calculate to tell people whether it's true or not. So after my calculation, I make the conclusion whether it's true or whether it's not true. Whether it's independent or whether it's not independent. Okay? Nothing else I want to talk about for this chapter. Like the questions are too easy for the next two. Like I like my two examples better here. Okay. I like those two examples, which is no. 9H is not something involved in the curriculum. It's just something for fun. Next week? No. I don't think so. Yeah, next time.